let's get into it! So today, we will be pinpointing the pseudo-foci of this polar curve called the rhodonia, or simply a rose curve. As the name suggests, the rose curve presents a shape that resembles a flower with some number of petals. Generally speaking, it may have 4 petals, 3 petals, 8, 5, or even 69. But how these flowers are drawn are based upon the polar function of r theta equals sine of a theta, where a counts the number of petals. But more precisely, if a is odd, then there are a petals. And if a is even, then there are 2a petals. If we compare a full rotation of the polar curve of a equals 2 and a equals 3, then we could see that the a equals 2 curve creates a new petal for each oscillation, while the a equals 3 curve also creates new petals, but after that, redraws the whole rose curve. But despite this odd behavior of this petal generation, the geometry of these petals suggests that the pseudo-foci must lurk under the outer reaches of the curve. And since the number of petals vary by the variable a, we should expect a different number of PFs to pop up for the sake of this mere variable. Since we will have varying numbers of PFs, we can only anticipate how much labor the 3-step rule would bring us. Speaking of the 3-step rule, let's begin our search for pseudo-foci through step 1. With our polar function r theta equals sine a theta, we must evaluate its first to third derivative. Before doing so, we notice that the function has a variable a inside sine, so I decide not to shorten the trig functions yet to emphasize that we need to carry over an a through chain rule when differentiating. By utilizing that rule, our derivatives would be as follows: a cosine a theta, negative a squared sine a theta, negative a cubed cosine a theta. Since taking the next derivative creates an extra a, then taking the 100th derivative do be sounding like sine of a theta. And now is when I shorten the variables, making them look like these: s sub a c sub a, negative a squared s sub a, and negative a cubed c sub a. Whereas s sub a and c sub a are, you know. But overall, that will do for step 1. Alright, after completing step 1, we shall now move on to step 3. Whoa, what happened to step 2? Well, I decided I should do something different in this video for clarity reasons. But zooming into step 3, we shall take our r, r prime, and r double prime expressions and replace them with the corresponding terms in the evolute parameter. Now, a short note that I want to get across the algebra as fast as possible without losing its significance. So, plugging in the expression leads us to this parameter. Simplifying does not do much to this expression, but this will reduce to s sub a c comma s plus s sub a squared plus a squared c sub a squared all over s sub a squared plus a squared times c sub a squared plus 1 times coordinate negative a s c sub a minus c sub a, comma a c sub a c minus s sub a s. And when we plot this parameter, a web-like shape appears, which is formed by these cusps. It is somewhat intuitive that the generation of these cusps lie under the petals of the rhodonia, but it is not too intuitive that there are cusps in between the petals, which to me sparked some interest. Because the reason these cusps exist between the petals is, during the transition to each petal, we will see this flat subcurve that crosses the origin. And since flat curves have a low curvature, we expect that each of their evolute cusps must be far away from them. But overall, these phenomena are better visualized by drawing the oscillating circle of the rose curve that connects the evolute and the rose. In doing so, we see that the circle gets so small during its heavy runabout inside the petals because of high curvature, while in contrast, the circle gets so big during its easy transition past the origin because of low curvature. But you know what the cool thing is? When the rose has so many appendages, this behavior from the circle gets so extreme that it spasses out. But now that you have some visual insight of how these cusps are formed, you may have some idea at which values of theta yield a pseudo-focus. And this is where step 2 comes in, where we rationalize that idea. Again, this is a step where we rewrite this lengthy equation with the derivatives we have, and solve it. And since I want a quick run through the algebra, the equation will look like this. After some simplifying 2 hours later, this entire footlong gets pressed into a finger sandwich that is c sub a s sub a times 2a squared s sub a squared plus 1 equals 0. Now, since these are 3 products equaling 0, we can separate them into their own equations. And hey, look at this! We have sine a theta equals 0, then cosine a theta equals 0 for the solutions. These two make some sense because whenever sine a theta or the rose curve hits the origin, we would get those pseudofoci from those flower curves. Similarly, whenever cosine a theta equals 0, sine a theta or the rose curve either hits -1 or 1, where we would get those pseudofoci under each petal curve. Because of this relation, we have some insight into what solutions might come from these equations. And to start, since what A does for the Rodinia is compress its rotation, a single cycle of the curve should be 2 pi over A. And since the curve returns to 0 twice in one cycle, then we will get a 0 for every pi over A radians until it hits 2 pi. And so, with the help of the visual, the corresponding solutions of sine a theta equals 0 would be pi over A, 2 pi over A, 3 pi over A, up until 2 pi. And then for cosine a theta equals 0, those will be in between the sine solutions, so they would be pi over 2a, 3 pi over 2a, 5 pi over 2a, up until 2 pi minus pi over 2a, because sine already occupies 2 pi. Okay, since we have these two equations taken care of, how about this third one? Well, that one doesn't do shit. This is because no solution exists for this dingo. Can you really add a square number with 1 and equal it to 0? If you thought about it, then of course not. So basically, step 2 is done for. After that, we shall proceed to step 2.1, which checks if our inconstant amount of solutions are extraneous. But hey, remember from last episode that I said step 2.1 is optional and is only recommended when there's a cusp on the polar curve? Since our rose doesn't really create a cusp, then we definitely should skip step 2.1 and not plug those solutions. Ah, psych! Who am I kidding? Let's plug in these derivatives, shall we? When we do, the expression will look like this. And when we simplify, the equation results to s sub a squared plus a squared c sub a squared plus a squared equals 0. And hey, look at this! We have another set of squares equaling 0. Do not overlook, but whatever happens, this equation will never equal 0. So with respect to this fact, there exists no extraneous solutions, which reinforces my statement of optionality. Now that we acquired our real safe-to-go solutions from step 2, we now go back to step 3 and plug all of these things separately into our evolute parameter. Actually, no, we don't, because there's actually a trick behind all this. And that trick is plugging in the step 2 equations of sine a theta equals 0 and cosine a theta equals 0 as is. By plugging in one of these, not both but one of these, we represent the half of solutions that are derived from that equation. So for example, let's start with the equation where every sine a theta or s sub a is 0. If sine a theta is 0, then cosine a theta may either be -1 or +1. But we're not plugging that in. But we can guarantee that any cosine a theta squared out there is +1, right? Because of that, we are set to plugging into these terms. When we do, the parameter turns into this. When we simplify, the parameter turns into this, then turns into this. A over 2 c sub a times -s comma c. However, there are still the leftovers of cosine a theta, negative sine theta, and cosine theta. So what do we do with them? Well, I simply reduce each theta to this variable I'll bring up as big S. And big S represents all the solutions that came from sine a theta equals 0. Since we do not have a strict amount of solutions, we really can't do much but represent each changing solution. So in the end, we will have a over 2 cosine a big S, negative sine a big S, comma cosine big S, which are the pseudo-foci that lie outside the polar curve. Now the inside pseudo-foci, which are those from the solutions of cosine a theta equals 0. Like before, every c sub a will be replaced to 0, and every s sub a squared will be replaced to 1. By doing so, the parameter turns into this. Then, as I acquire my simplified result, I will replace every theta from the shorthand variables to big C to represent the solutions of cosine a theta equals 0. So in the end, the parameter will be the pseudo-focus coordinates of a squared over 1 plus a squared times sine a big C times cosine big C sine big C. And finally, we have the last set of pseudo-foci which reside inside the rose curve's petals. And so, we have all our pseudo-foci. Heh, you think I'm done with that joke? Nope. But speaking of being done, thank you so much for watching this video, and I hope this example video finds you with some interest in polar curves. But I don't think I have anything to say anymore, so I think I'm gonna end it here.